In the previous lessons, we have learned different cases for electrolysis, and we have used the 4 steps method to analyze the what's a product going to be produced in each case. So in today's lesson, we are going to talk about the industrial application of electrolysis. So how do we use electrolysis to help to solve some cases in our daily life? So there are 2 wide applications for electrolysis in our life. The first one is called electroplating, and the second one is a purification of copper. So let's focus on the first one, electroplating of metals. So in grade 10, we have a unit talk about corrosion of different metals. A lot of reactive metals, it can corrode quite easily. So to avoid that, we can have a thin layer of unreactive metals on the surface to prevent it from corrosion. Okay, that's one of the reasons that we need to do electroplating. And sometimes, if we want the object to have a silvery, shiny, or golden look, we also do electroplating to place a thin layer of silver or gold onto the object that we want. Okay, so in order to do electroplating on any object, not any object, but the object need to be able to conduct electricity, otherwise it won't form a closed circuit. So the setup for the electroplating of metals is that we place the object that we want to be plated at the cathode, and then the plating metal. Okay, for example, if I want to plate a silver layer onto the object, then I would place a silver rod. Okay, so the plating metal as the anode. And then we need the electrolyte. The electrolyte must contain the ions of the plating metal. Okay, so we need an aqueous solution of a salt that contains some plating metal ion in it. Okay, so here is an example how we do electrolysis. So in this diagram, you can see there is a key. That's an object we want to plate a silver layer onto it, and then we place the silver rod, which is a material, at the anode, and then we have the electrolyte, which contains the silver ions in it. So in this case, we use silver nitrate solution. Okay, so what's going to happen in this setup is that we have, from the negative electrode, it will send electrons to the key. Okay, and there are loads of silver ions in the electrolyte, so those silver ions will be attracted to the key, and it will gain electron and then place a silvery layer of silver on the key. So that's what's going to happen. Okay, so at the anode, we can write half equation at the cathode, which is the object we want to be plated, we can write an equation to represent that. So cathode, we have silver ion in the electrolyte, which gain electron to form silver metal, which is plated on the key surface. Okay, remember to write the state symbol. Okay, so we constantly moving or removing silver ions in the electrolyte. So to keep this process continue, we need to replace those silver ion in the electrolyte. So at the anode, we have the silver rod which lose electron and form silver ion. Okay, so silver as a silver rod will lose electron and become silver ion and lose electron. Okay, remember the state symbol. Okay, so in that case, it replaces the loss of silver ions in the electrolyte. So for part B, describe the concentration change, if any, of silver ion in the electrolyte and explain your answer. So as I mentioned, although we constantly removing silver ions in the electrolyte to play the silver on the key surface, we also constantly having silver on the silver rod to lose electron and replace those silver ion in the electrolyte. So overall, the concentration remains unchanged. Okay. So the concentration of silver ion remains unchanged. Okay, so as the rate of forming silver ion as the anode is the same as the rate of consuming silver ion as the cathode is the same. Okay, so that's for part B. And for part C, from this question, can you conclude whether anode or cathode should be the metal? Okay, the metal that is used to plate the object. Okay, so not the object that we want to be plated. Okay, but the metal. Okay, so if we don't remember the setup, we can also deduce the answer. Okay, so what's the metal here used for? For example, in this case, we have silver. Okay, so the purpose of having a silver rod is to replace the lost silver ion in the solution. So the metal, we wanted to provide more silver ions for us. So it will undergo this reaction, so from silver to silver ion. So in this reaction, the silver lose electron to become silver ion. So it undergoes oxidation reaction. Okay, so remember, oxidation reaction takes place at the anode. So that's why we put it at the anode, not the cathode. Okay. The reason for that we can write like this is because silver layer is formed at the cathode. Okay, so object to be plated should be connected to the cathode. Okay, and the metal at the anode will preferentially discharge to compensate the loss of silver ion in the electrolyte. Okay, so that's the first application, electroplating of metals. Now let's move on to the second application, purification of copper. Again, in grade 10, unit 10, we have learned different ways to extract metal. So for copper, we can usually extract copper from its ore using hydrogen gas or carbon monoxide. Okay. However, the product that we get from these methods is only 99% pure. Okay, the number seems promising. However, in reality, the impurities actually would reduce the electrical conductivity of copper significantly. So we want to get rid of that 1% impurities. So what are these 1% impurities? They are mostly silver, gold, platinum. Okay, these are unreactant metals, and some iron or zinc. These are metals are more reactive than copper. Okay, so we could use these setup to purify our copper. So how do we do it? So we place the impure copper rods as the anode, okay, connected to the positive electrode, the anode. And after we complete the circuit, what's going to happen is the more reactive metals, and also including copper, it would lose electron and then become ions. So if, for example, we might have, okay, assuming a little bit, we might have copper 2 ions formed. Okay, and remember we have some impurities as iron and zinc, so we may have also zinc ion formed. Okay, so these are more reactive, these are quite reactive metals, so it's gonna form ions in the electrolyte, lose electron. And for gold, silver, or platinum, it will not readily also prefer to lose electron, so it would just fall down as impurities, and you would find maybe some gold or platinums here. Okay. Okay, then after some time, copper in the solution, okay, would gain the electron, okay, from the negative electrode, okay, and then it will form pure copper on the surface. Okay, so that's pure copper formed here. And here you need to jot down copper only formed the layer of pure copper. It only formed in the areas in the electrolyte that have contact with the electrolyte. So that means you would not expect to see any pure copper formed here above the electrolyte. Okay, so please note that. So let's take a look at the questions related to purification of copper. So here in this question, it shows a setup to refine impure copper containing sand and zinc as impurity. So remember last year we mentioned the component for sand is mainly silicon dioxide, okay, and then zinc. So in this setup, when the circuit is closed, what's going to happen is that at the anode, okay, as anode we have the impure copper electrode, so it should contains copper, it should contains silicon dioxide and also some zinc in it. Okay, so silicon dioxide, it will not conduct electricity, so after some time silicon dioxide will just find at the bottom, okay, fall down, and at the bottom of the container you will find the sand. And then what's going to happen to the zinc and copper is that it's gonna lose electron and become copper 2 ion and zinc ion in the electrolyte. Okay, so we can write that down. So for A1, the reaction that's going to happen as impure copper rod is that the zinc metal would lose electron and become zinc ion. Okay, and also copper would do the same. Okay, that's as the impure copper rod, the anode. So what's going to happen as the negative electrode, the cathode here, this one. Okay, so which ion would be preferentially discharged at the cathode? Is it the zinc ion or the copper 2 ion? Okay, so there are two reasons why only pure copper will be formed here. Okay, so first, as zinc is impurity and we know it's only 1% impure, around 1% impurities in the impure copper sample, so that means, okay, first the zinc ion concentration is very low. Okay, that means it will not be preferentially discharged. And also, if we compare the reactivity of zinc ion and copper 2 ion, copper 2 ion would be preferentially discharged as copper 2 ion is a stronger oxidizing agent than zinc 2 ion. Okay, so to help you to understand this conclusion, we can always use this method. Okay, if we talk about the reactivity of metal, we know zinc is more reactive than copper. Okay, so for zinc, it would prefer to lose electron and stay as zinc ion. However, for copper, since copper has a lower reactivity, okay, so it's pretty unreactive, okay, and pretty stable. So that means copper 2 ion, on the other hand, is pretty reactive and unstable. So when we compare zinc ion with copper to ion will have higher reactivity compared to zinc to ion. So that's the reason why as a cathode we got copper to ion, which is preferentially discharged. Okay, so we can fill that in. For A2, it should be the copper 2 ion that gain electron to form copper. Okay, and then for part B, you need to describe and explain what will happen at the impure copper rod and the pure copper rod. So, according to the equation that we have written down, okay, so at the impure copper rod, we would find, okay, the size of the electrode would decrease. Okay, as zinc ion and copper 2 ion form. From impure copper rod. Okay, and zinc and copper are stronger reducing agent than hydroxide ion. Okay, so as a pure copper rod, okay, so copper 2 ion gain electron and turn to copper, so the size of the electrode would increase. As copper is formed. Okay, the reason is that copper 2 ion is a stronger oxidizing agent than zinc ion and also hydrogen ion. Okay, and the last question is if the waste from the electron plating in industry is released into the sea, what will be the problem? Okay, so the problem is that the waste may contain, okay, you can find more information on the next page of your notes. So the waste may contain acid or alkaline or some toxic substance. Okay, so here we are talking about some heavy metal ion and cyanide ion. Okay, and these toxic chemicals can kill marine life. So how can we solve the problem? Okay, what can we do to prevent those excess acid, alkaline, or toxic chemicals that is directly released into the sea? Okay, so in order to remove the acid or alkaline, okay, we can use simple neutralization reaction. And then for heavy metal ions, or let's use copper ions as an example, okay? So we can add sodium hydroxide, okay, to form copper hydroxide, which is a precipitate. Okay, and so that we can easily filter the precipitate. And before releasing the waste into the sea. Okay, so on the next page, it talks about the details of the pollutions that we mentioned in part C. So they're pretty straightforward and just some factual information. So I will let you to read, okay, on your own. And if you got any question, please, you can either message me or leave a comment on the Google Classroom, okay, or bring it up when we have the Zoom meeting. So that's the end of this unit, and please attempt the online MC questions, and the structured question can also be downloaded from the classroom.